in the last video, I introduced the idea of the Cartesian product, how it turns two independent spaces of possibilities, namely two different sets, into this one space of joint configurations, plus creating a new mathematical object called an ordered pair, right? So from that stage, from the stage that we're currently in, there's still no interaction, actually. No interaction between the coordinates A and B, right? They happen to stay within this box independently, right? In other words. So the Cartesian product contains every possible pairing of the choices that A has and B has. But, well, at this stage, though, it doesn't really tell us which combinations are meaningful, which combinations are worth taking into account and really look at. And this is actually where we're going to introduce the idea of a relation, a mathematical relation, because that's exactly when, I guess, it's a natural progression, right? All these ideas. So let's introduce the idea of a relation. R, we typically call it R, and well, the R is going to be simply a proper subset of Cartesian product between two sets or two possibility spaces, right? So this looks like it's nothing, but actually there's a huge structural transition from just talking about the Cartesian product and going into the mathematical relation of those this new space we have, right? Because a relation, the subset introduces this, I guess, the idea of selecting a region, okay? Because that's exactly what it's doing. A subset would focus. So here we have this new space called this A times B, the Cartesian product, and the subset and the relation, right? Relation in this picture is going to represent a singular small region within this A times B. That means that we have an additional predicate that we establish for this statement, so that we could pick a little boundary within that space and create a region. So you know that a singular set is based on a predicate. That is a very important thing we've been talking about, you know. But then now we have an additional predicate. So we have two predicates this time. Okay. So let's just suppose that A is a set of people and B is a set of cities, right? I'm going to give you an example. So A is a set of people, and B is a set of cities, right? So if you were to take the Cartesian product of these, I guess, sets, you're going to end up having a person and a city, right? So this represents the ordered pair. Okay, and that condition selects some ordered pairs and rejects the others, right? So the selected pairs, so the ones that would correspond to true, again, this is the predicate. This is like a predicate, I guess we're creating a new predicate, is going to correspond to this relation. It's going to form a relation, okay? So again, a relation adds a new predicate, B. So we're no longer only asking whether A belongs to A or B belongs to B. We would ask, does A stand in the particular relationship to B? Are these two elements connecting in a way that the new predicate tells me? Okay, so this is why relations require Cartesian products first, right? Cartesian product is definitely it's more fundamental than a relation. Because before we can constrain possible interactions, we need a space containing the possible interactions first. And that space is called the Cartesian product. It's created through that. And then we constrain the possible interactions through introducing a relation, introducing a subset or a subregion within that whole space. And in further mathematics, like linear algebra, topology, this idea, the structural, map is going to be present. Trust me. I guess this is like one of the most fundamental mathematical spaces we've created through, again, introducing the Cartesian product. But this is it's some cool structural way of seeing mathematics. Okay. So a set gives us possible objects, possible independent objects, and the Cartesian products gives us the possible configurations of multiple objects from multiple sources, and a relation selects the configuration satisfying this predicate, this additional rule they have. Okay. So again, one thing that really structurally makes a difference between a set versus a relation is that a set has a unary predicate. Unary predicate. So only one predicate present for P of X. Sorry, for the set, let's call it P of X. But for a relation, we have a binary predicate. And we write it like this. So we get the predicate and we apply it to both of the elements within, right? So in that, in turn, this new additional predicate rule, relation would have more structure because now we have the idea of an order, because order matters for relations and the points, right? So take point X, Y. This is certainly not commutative. Y, comma, X. My bad. I just had to flip them, right? So this is simply true, right? You can't just flip them. You can't just flip elements inside or the coordinates inside the order pair. That's simply not allowed. So order enters the picture, whereas in a set, order does not matter, right? It's just a collection. If you simply put sets into I don't know, the description is going to be basically this combination, this, unordered way of describing objects, right?